And we start with invited speech by Professor Hynek Hermansky that will be chaired by Elmar Ned.
Welcome again, everybody. If I were to talk about Hynek's achievements, I'm afraid we wouldn't have time enough for listening to his talk. Hynek received his Master of Science right here in Brno in 1973, and his PhD in 1972, sorry, and his PhD in Tokyo in 1983. He's affiliated with the Center for Language and Speech Processing at Johns Hopkins University, where he served as a director from 2010 to 2022. He's also on the faculty of Brno University of Technology. He's a lifetime fellow of the Institute of Electrical and Electronic Engineering, IEEE, and a fellow of the International Speech Communication Association, ISCA. He received in 2013 the ISCA Medal for Scientific Achievement, and in 2020 the IEEE James Flanagan Speech and Audio Processing Award. He was the General Chair of InterSpeech 2021 right here in Brno, and also the General Chair of the 2015 IEEE Workshop ASRU, and the Chair of the Technical Committee of the ICASP 2000. In addition to leading several Johns Hopkins CLSP workshops, he was also on the organizational committee of several other ASRUs. And for 10 years, he was the executive chair of our conference, Sex, Speech, and Dialogue. It's my great pleasure to welcome him, and today he will talk about why should we ask why. I'm really eager to forward to your talk.
Thank you very much. Thank you very much for inviting me here. And as Elmar already mentioned, I've been in speech for a long time, and I've been giving talks about speech for many years. So I decided to, without a warning and without telling the organizers, I decided to talk about something much more important than speech, which is how to make gold. Because I discovered the old notes of Isaac Newton. As you know, Isaac Newton was not only doing these things like gravity, but he also was very avid researcher worker in alchemy. And this is from his notes, really taken from, and you can see that he describes how to make gold out of various bodily fluids. So you put it in and then you boil it for a while, for 40 days, and then you get one matter, you get black matter, then you boil it for another 40 days, and you get a white matter, and then you ferment it for a number of years, and then eventually what comes out is a field of a stone which can be used for making gold. Why do I talk about it? Because actually I was joking. I'm not going to talk only about how to make gold, but also I want to talk a little bit about the speech. But if you see how the gold is being made, as I told you, starts with something. So Isaac Newton describes the process very nicely. And of course, there are some secrets here and there, because that's what alchemists like to do, is they keep a little bit something behind. But essentially, description of the process, what you put in, what is it that you are getting in the process, and at the end, you get a result. And result is gold. And if you don't get the gold, you try fiddling with the things. Maybe instead of 40 days, you do 42 days, and maybe you put a little bit more of one thing or another. But at the end, what you're looking at, am I getting gold or not? And I'm not sure if Isaac Newton got the gold. Most likely he didn't. But still, a lot of people worked on that, and you know, Prague was one of the center of alchemy. When you look at speech research, not everything, but a lot of papers are done in this way, in a very similar way. What you do is that you get as much data as possible, and then you sort of play with the inners of the algorithm. You change something here and something there. You change the architecture. You change the modules. You download something more from Hugging Face, and then you play with the fixed meta parameters, and then you train it in different ways. Change the number of the amount of data, and what you look at the end is what kind of error rate you are getting. And if you are not getting what other people are getting, you know that you may have a hard time getting your paper in the conference. So you play with it a little bit and change something here and change something there. And what you are optimizing is just like Isaac Newton and other alchemists were looking for the gold, we are looking for better error rates. Typically, as a scientist, we always say, if I do this and that, I hypothesize that I will get a better error rate. So, however, I mean, if you look at the example of Isaac Newton, you discover that this is not the only thing which he was doing. You know, this is the story that he was laying under the tree, and suddenly the apple fell on his head. And he was wondering, why is it that apple fell on my head? So this question, why, is very important, and that actually is the title of my talk, and we'll be repeating it over and over again. So Isaac Newton is saying, why is it that the apple is falling on my head? And in the process, he discovers gravity. I mean, you know, it's a kind of important discovery, right? But I kind of hypothesize that maybe by the same, I don't know, but by the same process, he might have been looking at a tree and says, you know, why is it that I see the apples? And then he discovered, wow, because apples are red, and the tree leaves are green, and I can see very nicely apples, red apples in the background of the green leaves. And he might have started wondering, what does it make that I can see the different colors? So why am I seeing red as a red and green as a green? And you know, alchemists, they always believe that you can take some material and put it apart. That's what Isaac Newton and others were doing by taking these bodily fluids and tearing it apart and then reconstructing it into something else. So he used the same principle. He said, maybe I can try to take the light in pieces. And this was the experiment which he did. What was already known, actually, that if you shine the sunlight on the say glass, first it was glass spheres, that you can see the rainbow. But what he discovered was that this rainbow actually means something, namely that what's happening is that light is coming white light consists of number of components with different frequencies, different wavelengths of the shaking of the photons or whatever is there, right? And he discovered that different frequencies are perceived as the different colors. So that was actually a very important discovery which wasn't known before. And as I said, rainbow was known, but nobody knew why the rainbow is happening. People saw that you can see the different colors on the wall when you are shining, sun shines on the crystal chandelier, but they didn't know why. But he did very sophisticated experiments. Here is one, which he took the white light apart, and then he tried to take out part of the spectrum. And he observed that what was coming out, that if he didn't take anything out, he would be getting white color. But if he took part of it out, as predicted, he had a hypothesis, if I do that, I will see a different color at the, maybe I can, here at the output. So this was the discovery. This is what is, when you're asking the question why, and not just asking, am I getting what I want to get? So the alchemy basically goes this way. You get some data, and then you describe how you process it, and then you sort of report if your result is better. And if better can mean many things, but typically what better means, am I getting better error rate? And as an engineers, we always want to improve the things. Are the things improving? And if they don't, you tune the whole process. Interesting thing is the scientists actually don't always have a hypothesis that things get better. Because if you start understanding the process, you may also say, if I do this, and if my hypothesis is correct, I should get worse. But people hardly ever do that, and you know it's very difficult to get a paper in a proceedings to say, I did this and things got worse. Though scientifically, this is a perfectly okay result and perfectly good process, because what we are trying to figure out if we understand what is happening, right? So scientists, they work differently. Scientists, they set up, they are asking question why. That's what the science is the highest achievement is to know why things are in a certain way. And I very much encourage people also in speech. It's not that, of course, people are different. I don't want to attack everybody who is in the field. But if you go to conferences like we just came back from Interspeech, most of the papers are like describing the process and describing the result. But in the old days, and even now, probably if you go to other conferences, people do worry about things like why some technique works, when does it break down, and why. What am I learning about the speech? You know, can we reuse this knowledge which we are getting? So those are the questions which the scientists should be asking. And so this was just a way of introduction, and I spent almost 15 minutes telling you that, but I think it is important. And that was an introduction to the topic of my talk. But you know, if you want to be a scientist, in the old days when I got in the field, the things were different, because that's how we were working. We believed that we build a system, and then there is some knowledge built into the system. And of course, this knowledge is being also supported by some amounts of training data. And to get the message, you have to put the knowledge in, and then you put in the data in. And here I just listed what MIT was giving as a course for speech recognition people. So there were a number of fields which people could work in, and essentially some of these fields are quite scientific, right? I mean, we have represent phonetics and linguistics and so on. So, but nowadays the things are different. What we do is that we sort of believe that all you need is to download the right amount, software, then you get your data, and then you train the system to get a message out. And you don't even need know much about the speech. As a matter of fact, I was a Japanese friend of mine was complaining they are getting a lot of competition from finance people, because finance people have a very powerful computing, and all they have to do is to download some program and download some data, and they get very good speech recognition. You don't need to know much about the speech. But anyway, so how do I want to behave a little bit like a scientist in the 21st century? So when I look at this picture here, I see big speech training data. So I decided to ask about the signal itself. Say, what is it that we do? Why do we speak in a certain way? What constructs the speech? And I'm just touching the tip of the iceberg here, but I just want to show what is it that we can get if we start asking questions about the speech signal. Well, we have to start go back a little bit in the history. And if you look at the history of the humankind, history of the humankind starts with the moment when the animals start getting out of the ocean. Because when they get out of the ocean, they had to start developing a different hearing organs to hear in the air. Of course, animals hear in the water, but now once you get out, you have to change. So it took about 200 million years to get from these first animals here. This is as is believed, one of the first guys who got out of the water. And this is a Homo sapiens, which is very much like us. It looks a little, no, actually looks very much like us. Definitely, this guy has the very similar hearing organs as we do. And of course, the hearing evolved to survive. They didn't speak it. They evolved the hearing in such a way that they could protect themselves, they could hear what's coming, what can eat them, what they can eat, and so hearing was there suddenly. And then Homo sapiens maybe decided maybe that would be a good idea to start speaking. And there was about only 200,000 years to evolve hearing. So 200 million years evolving, hearing. 200 million years evolving hearing, but 200,000 years evolving speech. So my hypothesis is we learned to speak in such a way, actually my hypothesis, that was Roman Jakobsen, a big professor of Masaryk University here also, right? He made quite a bit of career here in Brno. They were saying we speak in order to be heard, in order to be understood. So there is a purpose in speaking, and you see the important part is we speak in order to be heard. So we start evolving the speech built on the properties of hearing. So the hypothesis which I try to follow here and maybe justify it a little bit is that human speech evolved to fit properties of human hearing. And we'll see how far we can get with this hypothesis, or how convincingly I can convince you that maybe this hypothesis might be somehow supported. It is a hypothesis. I'm not saying that this necessarily must be is totally verified, but all what I'm seeing is that it's very likely. So we have to look at the first. We have to start looking at the hearing. What is it that hearing is doing? The first thing is that hearing is doing spectral analysis. This happens very much in the periphery, just in the ear. So ear is, of course, not the only thing which contributes to hearing. It's just the periphery. But at the very beginning, we are doing spectral analysis. We take the signal, and very same way like Isaac Newton was separating different colors from the white light, we are separating different frequencies from acoustic signal. And people always say, of course, we know it. I mean, forever we are doing, we all look at spectrograms and we do spectrum and everything. I say, no, it's not exactly what hearing is doing. Hearing is not computing spectral envelopes. Spectral envelopes is such a fragile thing that it would be ridiculous to use it for getting information from speech, though we all do it. I mean, but if you look at it, I mean, hearing people tell you ridiculous. Hearing is there to separate components of the acoustic signal into individual frequency channels and then process it individually within these frequency channels. How do I know? Well, why do I think so? Because if you look at the whole process of hearing, here we have it. This starts at the cochlea, at the periphery, and that's where different parts of the cochlea are vibrating depending on the frequency components of the acoustic signal. But then it goes through the wires, through the neurons, all the way through the process, through a number of processing stages to the auditory cortex. And auditory cortex has the same tonotopic organization as you see on the cochlea. Why is that? Because different parts of the brain are processing different parts, different frequency components of the signal. So this is why we are having hearing which is frequency selective, because we want to separate the signal into different frequency channels and ignore the channels which we don't want, or which are corrupted, or which don't carry the information which we want, and focus on the channels which do carry information which we want. By the way, that's the whole animal kingdom is doing the same thing. I mean, if you look at a little moth which is escaping the bat which wants to eat it, that moth doesn't hear everything. He only hears for the frequency bands where the bat is emitting when it's chasing the moth. Is using the echo, right? So everybody is doing that, including human beings, and including when we are listening for speech. How do we know? Because we can do experiments. This is an experiment from Bell Laboratories from the first half of the last century. Harvey Fletcher first, and then a number of other people. They did what is called frequency masking. What they did, they took a signal of certain frequency, tone maybe, and then they were corrupting it with a band of noise, which was getting broader and broader and broader. What they discovered, very interesting thing, as they were getting a band of noise broader and broader, they could hear the tone worse and worse. They have to make it stronger because the noise was what is called masking the tone. But after a certain point, no matter how broad the noise was, the masking didn't increase anymore. So what it says, that was, first thing wasn't very interesting, which was like if I add some more noise into the signal, I hear worse. But what was incredibly interesting, that at a certain point, in this case 400 hertz, when the band of noise was 400 hertz, when I went beyond 400 hertz, I was getting more and more and more energy of noise, but it didn't matter. Why? Because it started hitting a different frequency channels. So this is a very convincing argument for the role of hearing, frequency selectivity of hearing. Because what you really want, what happens outside this critical band doesn't matter for detecting the stuff inside the critical band. Only what happens inside the critical band that counts. So this is an ideal property if you think about it, if you are building a system which is robust in noise, because very often maybe half of the spectrum gets corrupted. And what we can easily do, we just ignore it because it doesn't matter for the part of the spectrum which is inside the frequency bands. Another masking experiment is what is called temporal masking, in time domain masking. In this experiment, masker, the noise maybe precedes the signal, and what you see is the masker is close to the signal, there is a lot of masking. And as the period between the signal and the masker is increasing, the masking is decreasing up to the point. After 200, 250 milliseconds, it doesn't matter anymore, basically, forget all about the masker. So again, we have the critical time interval, which seems to be saying, well, we have some buffer, and as long as the things fall in the buffer, then they interact. But if they fall outside the buffer, they don't interact, they don't matter. So this is another wonderful property of human hearing, is that we have a frequency selectivity and we have a temporal selectivity. So, and of course, temporal selectivity shows in very important way, which recently people start looking into it much more, which is that we are specifically sensitive to certain rate of change. This is experiment again from Bell Labs from 1923, I believe, where people showed that we are most sensitive to rate of change when you modulate the signal with about a 4 hertz envelope. 4 hertz, of course, is 250 milliseconds in time domain, right? So it says basically you are most sensitive if the wave which shows you the modulation envelope falls into this buffer. And this is actually a very useful thing. We will see that we can use it for dealing with some signals to improve the robustness. So we have a temporal frequency selectivity, we have a temporal selectivity, we have a sensitivity to modulations. Let's see how do we speak then. So how do we speak is that we discovered that we can use the organs which we use for much more useful things like biting and eating and breathing. We can use it for speaking. That's what I think Homo sapiens suddenly discovered, and look maybe around that other animals do the same thing. As you move the vocal tract shape, you can generate the different speech sounds. You can also generate different speech sounds by changing excitation, but excitation is kind of secondary. What really counts is the shape of the vocal tract. So we use it, so message is carried in the changes of the vocal tract shape, which modulate the spectral components of the source. That's what Homer Dudley in 1940 was saying in his very, very influential paper, which actually also brings me to a point where I want to remind our people that not only things which happened in the 21st century and not only things which happened in the past 5 years, but also things which happened a long, long time ago. Homer Dudley was one of the geniuses of the speech processing, I can tell you that. And he was saying things which engineers very conveniently forgot all about. You know, because what he says, message is carried in the changes of the vocal tract shape. Don't worry about the source. You can whisper, or you can, it doesn't really matter. You can speak high pitch, low pitch. Message remains. First, basically, most important components of the message are in the shape of the vocal tract, because that's how we generated the different speech sounds, different phonemes. But what happens also if you change anything in the vocal tract shape? You can, if you study the speech production, you discover that any small change in the vocal tract shape is always reflected in all frequencies of the spectrum. This is very interesting. I close the lips, and I know that all resonances of my vocal tract will go down. I put a constriction somewhere in the back, and some of them go up, some of them go down. Basically, there will be a different lecture to talk about it. But what is important, any change in the tract shape is reflected at all frequencies. And if you look where the information about speech sound is, this is an experiment which we did a long time ago when I was in Oregon. You can see that information is everywhere, except for very, very low frequencies. But from like 300, 400 hertz up, everywhere there is a speed, maybe a little bit less at 15th critical band. This is the Bark frequency scale, but more or less everywhere. This is, of course, very good. And again, it was well understood by people who work in telephony. 20th century, early 20th century, people start running experiments with filtering the speech, with the high-pass filters and low-pass filters, adding a noise. My friend John Allen is claiming that the experiments took about 40 years, and actually probably they did. It was, for the longest time, it was highly classified. Only after the war, the major papers start coming out on the work which was done since 20s of the 20th of the last century. What people were discovering is that you don't need the whole spectrum at all to communicate by speech. It's very interesting. You communicate in a way that you divide your signal into this, what they call articulatory bands. Each articulatory band is about 2 critical bands. And if you take the half of the spectrum, you still get a very decent recognition rate, about 68%. And if you take the other one, you get the same thing. You get also 68%. So half of the spectrum gets me 68% of the correct phoneme recognition, which when I add on top of that all the knowledge about the language, I can perfectly communicate. That's what people also showed. So I need only half spectrum for the perfect communication. Even more, if you cut at random these articulatory bands, you can still get 68%, because what really counts is how many these articulatory bands I'm preserving in order to communicate, and still get a 68%, and still get a perfect recognition, perfect communication, or very reasonable communication. So again, I mean, if I'm worried about the robustness, this is something I should really be paying attention to, because it says I can easily leave out half of the speech and still get a useful signal. And if, by the way, you sort of are following what's happening in the world now, in the world of speech recognition, if you are designing wave-to-wake processing, that's how you do it. You maybe cut out part of the signal, and you try to predict what you cut out from the rest. So basically, these people, unfortunately, hardly ever refer to this original work from their laboratories, but essentially they are using it. And it took us about another 100 years to discover that. We don't need all the frequencies in order to communicate, and frequencies which are missing, or information which is missing, can be predicted from what is left. So please think about it a little bit. I have only a few minutes to tell you, but it's very important if you are interested in robustness, and it's becoming more and more important, because that's what it started with, the fact that people were training the recognizers, leaving out parts of the frequency, some of the frequencies. It's called spec arc or something like that, right? And they discovered they can even train recognizer better. They definitely build a recognizer which is more robust. They use this principle. Anyways. If you have any questions, if there's any questions during the talk, please, I mean, just we can, I want to make sure that this is understood. So we clearly are spreading the information in frequency in order to make the speech signal more robust in presence of noise. And we use the spectral selectivity of human hearing, and we figured out how to do it by changing the shape of the vocal tract, because that's how we put all the information at a full spectrum, but we don't need a full spectrum. We can easily leave. So that much for the importance of spectral envelope. If you can leave half of the speech out and put in noise or put in actually empty, nothing there, and you still communicate, it tells you something. Another interesting, so this was frequency. Now we have about time. In time, as you see here, I mean, I played only maybe a little bit of that if it plays.
When the sunlight strikes raindrops in the air, they act as a... When the sunlight strikes raindrops
Now I
in
don't
the
know how
air,
to
they
stop
act
it.
as a prism and form a rainbow. When the sunlight strikes raindrops in the air, they act as a prism and form a...
Okay, thank you. Because that's what worries me always when I don't use my own computer, then I lose a lot of control. But what you could see here is that vocal tract is moving relatively slowly. It's not moving very fast because it has a quite significant inertia. We cannot move things very fast, not even with the hand, right? So the dominant frequency of changes is about where we hear the best, about 4 or 5 hertz. Then we know you can measure, if you measure the movements of the vocal tract, that's what you will discover. So, but as a consequence, if I want to produce sequence of speech sounds, what you get not a sequence of speech sounds, but you get something very kind of blurry. The intended speech sounds basically blur into each other. And for longest time, people say this is the biggest enemy of a machine recognition of speech. Not anymore, I tell you why, but I mean, because interesting thing, and of course, this is known since 1940 when people discovered the use of spectrogram in speech research. This is one of the pictures which phoneticians don't like to see, because this is ki, ku, ka, and what this is a k, this is a k, this is a k, those are the spectrograms. And the k's are so different depending on what follows, which vowel follows. The people said, well, never ever we can recognize phonemes like this because of coarticulation. And we'll see that we can deal with that. Extent of coarticulation you can actually measure. We did it here in Brno with Katja Yegorova, and we actually started looking at it a long time ago at Johns Hopkins. It's also about 200 milliseconds. After 200 milliseconds, kind of the effect of the first speech sound sort of decays enough that the second speech sound is seen a little bit clearly. So what we see here is a distance between a point here and point far away, and you see that if once you move the point far away about 200-300 milliseconds, it doesn't matter because you already are guaranteed in average to be in different speech sound. But as long as you are close, I mean, you are always influenced by the sound here. Very similar phenomenon as the temporal masking, this time is done with speech. Very interesting. You can also look actually here. Now I'm maybe pushing on you the evidence why I sort of think that things are the way they might be. What you see, look here is the mutual information about the points in a spectral plane, in time domain, and the labels of the speech. You can do the experiments called mutual information. You can ask how much information is in certain point of the spectral plane with respect to what we are after, which is like speech sounds. And you can see this mutual information spreads for about 200 milliseconds. Right, another decent combination. This is an interesting thing. I decided to spend one slide on this, which is like co-articulation is not bad. Co-articulation is good as long as you are a human being, or as long as you are advanced, sophisticated speech recognition system, which we now are building. Because what you can see here, in this experiment was actually took quite a storm. If you try to recognize the vowels, it was did, dat, doet, this sort of thing. And if you take the whole syllable, of course you get very perfect recognition, right? if you cut out only the vowel, you get worse. Even when you are asking people, can you please recognize what I'm showing you? People don't get that good, 15% worse. Because once you start missing these things where the co-articulation spreads, you can't decode the speech so well. It's even worse is that if you cut out the vowel and only keep the consonants, co-articulated consonants, you get even better, or at least the same. I mean, 90% accuracy, 85% accuracy. So you cut out what you want to hear, and you leave out what you think you basically is being disturbed by this vowel, and you hear better. Very interesting. I mean, sort of. So what I'm saying is that co-articulation is there to spread the information in time. So any decent engineer, if you want to communicate in noise, presence of noise, you try to spread the information into a number of components, and we can do it in the frequency, and we can do it in time. So the way we are speaking is actually very smart, because we are putting information not only in, because if you believe that information about speech sounds is important, we are spreading it around. Here we have a little picture, just to summarize. In production, every change of the tract shape is reflected at all frequencies of speech spectrum, and a tract shape doesn't change very fast. In perception, hearing is frequency selective, so it can pick up these pieces of information, put it into different frequency channels, and if one of them gets corrupted, you just ignore it. And hearing has a significant inertia. So again, I mean, we are putting this whole co-articulated pattern into our buffer and using it for recognition. And if part of that gets screwed up, I mean, we can still use the other part. Okay, this is how we are communicating. I know this is maybe a little bit noisy picture, but if you want, I mean, you can look at the paper which came out of speech communication, and you can start thinking about it to what extent I'm right or wrong. Sequence of sounds goes in through vocal tract inertia, gets spread in time, then through the action of the vocal tract, it gets spread in the frequency. So what we get, information is here. And goes out in the signal. It gets screwed up by various means. Speech is corrupted in the channel. So what we get here, but we form the different frequency streams here, and we put this information from different frequencies into our temporal buffer, and what we get out is the different ways of describing what was here at different frequencies, and by using a smart fusion, we get out the sequence of sounds. I know it's a little bit fast, but I think that if I want to end in, I have 45 minutes of
plus discussion.
Sorry, plus discussion. Yeah, so I have to do it because I wanted to get you a little bit. We are engineers. I mean, you know, so I'm not claiming that I'm a speech person. I'm not claiming that I'm a psychologist. I'm certainly not claiming I'm a physiologist. I'm an engineer. I would like to build better machines. So let's look at engineering. And actually, it's very interesting because speech is one thing. That's what I learned from our friend Fred Jelinek, late friend Jelinek. He said, data don't lie. Whatever is in data is true. I mean, you know, people lie, but not that intentionally lie, but people basically make conclusions and write the things in the papers. But if you look at the data, that's what you see there. This is what is there. If the speech evolves to be heard, properties of heard speech must be imprinted on human speech. So I have to show it, right? And if I look at a well-trained speech system, I should be seeing properties of hearing, even without putting it in. So this is, of course, I mean, you know, we all know that people start looking at the speech signal and say, well, I can now put the speech signal in, and there is this convolution of filters at the beginning of the system. If I look at impulse responses and transfer it into frequency domain, I get a bands, the frequency selective bands, and these are the frequencies which follow, which which are center frequencies of this bandpass filters, which we created without any intention of building a system which is frequency selective. The intention was that it should recognize well speech. And we put in a speech signal in. Number of people did these experiments. This one is from Johns Hopkins, from Pega Garimani, but number of people, actually Pallas was the first one, I believe, but number of other people did the same experiment. So this is something which is without question. These convolutive filters at the beginning of the, or linear filters which of the beginning of our speech recognition deep neural net, if you look at them closely, you get the bandpass filters, and these bandpass filters behave very much like a human hearing. Well, this is very interesting, right? In time, this is, again, one of the experiments. There is not that many experiments in time, but they are coming. And I have more evidence, but I show you only one which came from here, from Brno laboratory. What we did was we would just put in the convolutive filters at different frequencies. They were fitting it in, and then we looked at the frequency responses of these filters. And they are all bandpass, or pseudo bandpass. This is a derivative of the bandpass. No, I'm sorry, this is but these are the bandpass which have always peaked somewhere between around 4 Hertz. This is exactly where the human hearing is the most sensitive, but this is exactly also where the dominant rate of the change of the vocal tract is. So what we are getting out is what hearing is. We know hearing is doing. We know it since 1935, or whenever the first time people did experiments in selectivity to modulations. But we are getting these filters from the speech signal without forcing any knowledge of hearing. So those are impulse responses, and if you are interested in frequency responses, here they are. This is very useful, actually. I want to show the old experiment because at a certain point we accidentally. We were playing with various things, like just like alchemists. We put the bandpass filters on the time trajectories of the spectral energies, and we were changing the shape of the filter. And when we discovered if we use the filter which looks something like that, it actually helps us in dealing with something which is actually kind of annoying, which is like if you take original speech signal. This is a beat signal, maybe beat. And if I filter out in such a way that I will filter out all the Forman frequencies in E, so the E becomes pretty much like flat spectrum. You also hear beat. It's filtered speech, but E is certainly there. So if your system is working well, then you should get the same picture, but spectrogram definitely is not the same. As I told you, spectral envelopes are very, very easy to screw up. But if you put these filters which enhance, which suppress the DC and enhance the 4 Hertz, this is what you get. You get very similar picture from the both speech signals. So we figured out how to make the signal. How to make our recognizers a little bit less sensitive to changes in. At the time that we had the problems with microphones. This is actually those of you who were born before 19 or whatever, I don't know, 50. They remember Rasta, and Rasta was a quite successful technique at a certain point. This was the Rasta filter. But we saw these Rasta-like filters just getting it out from speech signal. That was the most exciting things. So if the temporal domain is important, we should be using not only spectral envelopes, but we should also use the temporal envelopes. So we came at a certain point in 1998, a technique which is called straps, where we were feeding these time trajectories of spectral energies from different frequencies into different neural net estimators. And then we merge this information from different frequency bands to get a final result. So there was very early deep neural net, I would think, because it was, you used rather long segments of the signal, about 1 second. it was very hierarchical. That's what people now do everywhere. And we did independent processing at the first stage of different frequencies. And we were getting some advantages, actually, from that. One advantage, which is very interesting for phoneticians or whatever, is that we also could think that we start dealing with this problem of K-K. Because if the K here in spectrogram was here in front of E and here in front of A, you can see that after using these traps and a trap-based recognizer, we could see that K is actually suddenly the same. So you can see if you use the sufficiently long segments of the signal and you train it, you use this information to extract the speech sound, suddenly co-articulation is gone. Okay, almost the end. Finally, we start looking at the two-dimensional pictures. So we are looking at frequencies, we were looking at times. Now we start looking into the whole time frequency plane. And it was also done, this experiment was also done here in Brno. Actually at Hopkins, but with people from Brno. So what we did was, what we discovered, we designed these two-dimensional convolutive filters. And this time domain segment is about 500 milliseconds or 1 second long. And what you are getting here are the impulse responses of these different filters. Actually, those are frequency responses, sorry. But what you can, bottom line, what you see here is that there is a number of them, and each of them is slightly different. It looks a little bit like what you are doing is that you are separating your time frequency band into different time frequency patches, and different frequency patches are paying attention to different components of the signal. This one looks at low frequencies, this one looks at that, and more like a frequency domain. This looks at the mid frequencies over time, and you can start looking at it and think what kind of this thing is showing. This is things like that are very often seen right there on auditory cortex, but I don't want to go into that. I couldn't help to put one slide which looks hopefully into future, which is like, if we want to recognize the speech, this is the way we should be doing it. Start with the signal, you take sufficiently long chunks of the signal, and you form the streams. And these streams are basically, each of them is different, paying attention to different frequencies and different times. And then you fuse it to get the speech sounds, and from the speech sounds, then you can get a sequence of words. And of course, people do, when in the fusion, you may doing this training with dropping some components in order to get some robustness. But basically, these streams are enhancing different parts of the I should say not spectrum, but time frequency plane of the speech. What helps you is something which I didn't talk about at all. So if you put a little bit block here, which we call performance monitoring, this is something which we work on for past 15 years. And anytime I try to submit the paper on that, sometimes it gets through, but very often the reviews, Hynek is showing it for a long time and it never works. So I just cut it off. But I still believe in it. But if we get a performance monitoring module, we can figure out the right way how to combine these streams. So okay, just going to conclusion. In 2012, I can't help to show when we will start looking at in a time domain and in modulations and the dynamics of the speech, I sort of start saying, well, if we start looking more into dynamics of speech, maybe a lot of things will start changing. Maybe we don't have to worry about co-articulations anymore. Maybe we start getting basically reasonable systems which will recognize the speech. And indeed, this is what I believe we are getting. So personally, I'm getting some inner satisfaction. 2011, it's not that we had it, but I saw, well, you start looking into right things, you might start seeing a better performance. We are using now long segments of the signal. Well, long meaning now maybe whole utterance, right? That's what goes into this deep neural that speech recognizes. Lower layers are frequency selective. That's what we see systematically. We train with leaving out parts of time frequency plane. That's how we get a wave to wake or whatever. So we are doing it. I mean, so you say, why, Hynek, why do you talk about it? I mean, we do it anyways. Well, I think there is a little bit of difference because finally we start understanding why it works. It's not only that it works, of course, if you are engineers, you want to get the best recognition rate, just the same way as the alchemists wanted to get the gold, it's fine. Your boss is happy, and you should be happy. And you get a paper in, most likely. But if you start understanding why things work, maybe you can do a little bit more of that, a little bit differently, even a little bit better. So hopefully, just to remind you, more we know, less we need to learn. We have a big problem is everybody says, oh my God, I mean, I can train this system once. I don't want to do it twice because I used, I don't know how many centuries of speech now in order to get a Google-like front end or recognizer, right? So more we know, less we need to learn. And how do you learn to more? That by asking, I believe you have to start asking questions why things are the way they are, not just reporting, this is the way they are, but why. So this is the topic of my talk, and I hope that I didn't bore you much, you know, so this is it, that's what I wanted to say. I'm becoming like a Trump, I realize. I mean, you clap and I clapping for myself. That's what we learn from politicians. I'm sorry, I've never done it before.
It was a wonderful
That was the
talk,
first
very
time.
inspiring, really.
Well, I enjoyed it.
For questions.
Hynek, what you were showing has to do with decomposing the signal, very much using Fourier transform. But you can also use different techniques, right?
Okay.
But the main assumption when you use Fourier is that there is no, it is stationary, right? The phenomenon to some extent. So my question is, do you think that if we use the different, especially nonlinear ways to decompose the signals, we can understand better
Can I
phenomenon?
go to the talk? Well, you know, I cut out a very big part of this talk because I was already running out of time. Because I'm not doing only that. Of course, if you use Fourier transform, you typically take a very short segments of signal and you go into time domain by providing a sampled version of the trajectory. But it's a legal thing to do. I mean, because, you know, typically you use 20, 30 milliseconds, and you say within this segment, things are stationary. Maybe I can compute the frequency components, given all the issues with windows and so on. But you provide a sampled version of the trajectory. But if I didn't cut out the part, and if I knew how to get into it, we are not doing only that. We are also now heavily using what we call frequency domain linear prediction, where we are directly modeling the spectral envelopes of the signal, no windowing whatsoever. It's not your short-term Fourier transform, but it's sort of looking at maybe 1 second segments of the signal, and you compute the envelopes of Hilbert envelopes in frequency bands and all frequencies. You get the very much, if I knew how to get there. I probably don't, right? Now see what, oh, this is what I wanted to show. You see, so what you can do is to model the envelopes. And what you get out, you get the envelope. What you get out is very much a spectrogram, except that in this case, this is a classical spectrogram. But this is a spectrogram which you obtain by modeling the temporal envelopes. So I'm sorry that I cut it out, but I thought I didn't want to confuse the, yeah.
Maybe this is a dummy question because I'm not really into ASRs, but maybe this effect of co-articulation, like incorporated in these systems, are one of the reasons why those ASRs are failing to identify pathological speech. So to kind of generate these transcriptions, what I mean that maybe like if the system is trying to incorporate this effect of co-articulation and deleting some stuff like vowels because they already know what's next. And then you have that the patient failed to do the onset of the sound or so. This could be one reason, or what do you think about it?
Well, the pathological speech is a pathological speech. So co-articulation may be a little bit different, right? I mean, I saw that, and this, still pathological speech is a co-articulated speech, maybe even more than the normal speech, because maybe you have a difficulties to move certain parts of the vocal tract. So you get, if anything, some of the sounds may be gone because you simply can't even produce them. I don't know. Maybe I'm not answering what you are asking. Is that pathological speech will be also affected by your ability to move the vocal tract. But in normal speech, we move the vocal tract in such a way that we can take advantage of this buffer. If you move the vocal tract a little bit slower, if you cannot move it with the right speed, then your hearing may have a hard time following it. Because we learn to speak so that it has the right rhythm, this syllabic rhythm about 4 hertz. In pathological speech, maybe, I don't know if you ever look at the modulations of the pathological speech, but it may be lower, I would expect. I don't know. I'm looking at Rafa because I know he may be doing that. So pathological speech is pathological, but I know we have to deal with that somehow. But if the phoneme is gone, maybe there is some evidence of person trying to articulate it, but we have to look at it maybe in different ways. Probably longer buffer, I don't know.
At least, we should maybe look at the people who are with people.
How
They perceive it, because learn. You have somebody with a stroke and he speaks, then and a person who doesn't know him
but
will not understand him well. At the same time, the wife of the affected or the husband will say, "Oh, he meant this and this and that," so they know.
But it's more difficult even for people who are with them to understand, because it doesn't follow the natural sensitivity of hearing. Because hearing, basically, the most important component is around 4 hertz. Buffer is about 250 milliseconds. We cannot make it longer. Maybe we could, but I really don't think so. This is what we were somehow born with, almost. So you can stretch it a little bit. But I guess that for pathological speech, we would need a longer buffer. I don't know. But as an engineers, we may be able to build it, right? Because, it's just a total speculation here, Paula.
Any more questions?
It will be more generic, but so you speak about we should also understand why our approaches works, and so until which point do you think we should go further error analysis, or let's say limitation sections in the papers?
Say it again. Are you talking about how to write the paper?
Not really, but even organizing our research.
Well, it's always up to you, right? I mean, so you are in charge of your research. Maybe what I try to push for is to fewer papers about just reporting the results, more papers about also maybe analyzing the results, analyzing the technique. But as I said, I mean, it's you want to get a paper in, or you want to keep your boss happy, and to get the paper in, you have to show the good result, and to keep the boss happy, you have to show the good result. So it's maybe not everybody has the luxury to sort of. Not everybody is an old professor who doesn't care anymore. So I have to be very careful. But in general, scientists are like that. They try to understand what is going on naturally. Sort of. So, but you may have a harder time getting paper in, yeah, unless we change the behavior of the reviewers, of course. And so I don't know if this is what I'm answering, but obviously you want to be appreciated, and you want to be appreciated by your colleagues, and you want to get a paper in, then you have to be appreciated by the reviewers, and unless we change the reviewers, we have to do what we do. Or if there is maybe more papers who sort of shows a little bit answers why, maybe reviewers, one day you will be reviewer, right? I mean, like it or not. So maybe that you can pay more attention to that.
I would like to thank you, Hynek, for emphasizing the why questions. Whereas Simon Sinek, in his Golden Circle, he says that start with why and then continue with how and what.
Yeah, I have seen his work recently, and I was actually almost sad because he started with this about 10 years after me. He got very rich. And I was saying this why since 1985 or something. But I never got as far as Hynek, because he made a career out of this. Yeah, I know his circles, and I don't know if people know it, but he says what, how, why, right?
Yeah.
And that's what. Yeah, that's. But I should show you some slides from 1985. I keep repeating it over and over, but as I said, I wasn't as skilled as he is to make a career out of that.
Yeah, but in general, I think that holds not only for speech, but
everything.
for text.
Absolutely.
We should probably continue asking then how to understand how in the 21st century to understand what's going on in deep nets, and how can we understand it, the structure, what's going on there.
I try to tell my students that if you ever try to convince somebody that you want to work on something, always start with the question, why do you do it? Because, naturally people do listen for that. And if you're writing proposal and if you don't say, why do you want to do this? Then, of course, in proposal, people may get a little bit upset. It's good to know why you are doing things, why. I had another slide which would be very appropriate for that. In general question, why? Actually, what happens? Can I show you another slide which I left out? Yeah. So this is a Richard Feynman, and he had a very nice speech. Actually, I encourage you to read it. It's a very entertaining thing. He describes the tribe in the Pacific, on a small island, where during the Second World War, American Air Force had built a base there, and they brought a lot of very good things, food and tools, and suddenly the islanders had a great time. And they say, of course, they are gods, obviously. But then at the end of the war, the Americans left, and they they build what is called a cargo cult. They start building the churches, which look like an airport. They would put in the watchtowers, and they would make I had a picture actually somewhere. They built the airplanes from the wood, and they were sitting there with the coconut shells on their ears, because that's what they saw. And they thought if they will do what Americans were doing, the planes will come again and bring them good stuff. And Feynman, because he says the scientists are sometimes like that too. They basically do the right things, but they don't know why they do it, because these Pacific Islanders didn't know why the things were happening. They just followed the procedure. And he says planes were never coming. And the scientists who sort of go and write the papers and go to conferences, but they don't know why, also may not ever see the planes. Really, that was a talk to cult experiments. So I had this slide, but I thought it wouldn't fit in. But since you asked, I mean, this is really very appropriate maybe to bring it up. Certainly, answering the question why, I agree with Hynek. Answering the question why, or starting with question why, is actually very important, because that helps your boss to convince your boss that she should let you work on the right stuff that you want to work on, and hopefully reviewers will also be looking for this a little bit more. That was my point. Thank you very much.
Thank you very much. I think this is a very good time to
Yeah.
end the discussion. It was very fruitful, and thanks.
Thank you very much.
Full talk. I learned a lot. It was amazing. Thanks a lot.
I had a good time.